Okay, the recorded started. Okay, so after recording, I will upload to the YouTube again, like the last time. Let me share my iPad. Okay, so let me show first the Borel 01 law that we described last time. So Borel 01 law, given this sequence of events, ANs are all the subsets of the sample space sequence of events. And then we consider this new event, which is written. Oh, my Apple Pencil doesn't work. That's strange. Okay, since the Apple Pencil needs about 1 minute charging, charge just before the lecture. Okay, so this new event, which says ANINO, ANIO means AN infinitely often, which is the point that belongs to AN, which is the event. The event means the subset of the sample space, which belongs to AN infinitely many times. So if you collect those points in the sample space, those subsets of the sample space is called AN infinitely often. And if you measure the probability of those events, then it's either 0 or 1. And the criteria that determines whether it's 0 or 1 is by looking at the summation of the probability of each event. If the summation is finite, then this AN infinitely often is 0, has 0 probability. And if the summation diverges, then AN infinitely often has probability 1. And we proved the first case. We haven't proved the second case, so I will finish the proof of the second case. And the second case is a little different than first case because it needs another condition. Another condition is that ANs all have to be independent. And this condition is necessary because I can give you right away the counterexample. In the example that doesn't satisfy the second case if ANs are not independent. So here is the example. Let's choose AN, A1 to be a certain arbitrary subset of probability 1/2. Okay? A1 is arbitrary subset of probability 1/2. And I will choose A2, exactly the same subset, A1. A2 is equal to A1. And from here, you already know that A2 and A1 cannot be independent because they're same event. They're not independent events. So they are same event. So A1 and A2 are same event. And now I choose A3, also same A1, same as A1 and A2. So I choose all the events AN to be same. It's all same subsets, same events, and they all have the, of course, therefore the probability 1/2. Right? And then what is the set AN infinitely often for this sequence? What are the points that belongs to AN infinitely many times for this sequence? So now I think we can, it works. This time it's lecture 13. I hope it's 13. And we were talking about AN infinitely often. So I'm giving you such an example. So A1, A2, A3, they can be all different. Okay. But yes. And if there, so for example, this point belongs to A1 and A2. This point belongs to A2 and A3, and so on. So you collect all the points that belongs to an infinitely many times. So it's an intersection of infinitely many ans. This is just these 2 points that I draw is just intersection of two of them. So they don't belong to this set. So an infinitely often is the point that belongs to infinitely many ans. That's the definition of this ANIO. And now I'm asking, if I define an to be all A1 for all n, then if I draw the same thing, then it's just same thing over and over again. We are A1, A2, A3, and so on. And I make this probability to be probability of this and P1 half. What are the points that belongs to an infinitely many times? So what are this event? This is exactly A1, right? All the points in A1 belongs to A2 and 3 infinitely many times, right? And therefore, and also if it is outside A1, then it doesn't belong to any of them, so it's hardly belong to infinitely many times, not even finite times, right? Okay, therefore, the probability of an infinitely many times is equal to the probability of A1, which is 1 half. This is not 0 and 1. This is not 0 or 1, even though the probability of the summation of all the probability, what is this? I mean, infinity, all of them. This is the summation of 1 half infinitely many times, because each one is 1 half. It's 1 half plus 1 half infinitely many times. There's a weird mathematics that if you add 1 half infinitely many times, you get finite number. But here it is infinity. Keep adding 1 half infinity. So according to the Borel Tantali lemma, the second one, since the probability, the summation of the probabilities diverges, this an infinitely often should be probability 1. But it's not, it's 1 half. Okay? And that's because those ans are not independent. So they don't satisfy Borel second, Borel Tantali second lemma, because ans are not independent. So we need the condition of independence. Good? Any question? Okay, now let's prove the Borel second lemma. And that one is a little bit longer than the first proof. Any question about the first proof? Okay, so how the proof goes? So we want to show that probability of an infinitely often is 1. That's the goal. That's the goal. So this is proof of second Borel lemma. So that's we want to show this with the assumption that the summation of the probability is that we will reach this conclusion. And what does this mean? This means we changed this last time often into this thing. So then we do the same thing. So what does, if some set belongs to an infinitely many times, then of course it belongs to union of a, let's say J from J greater certain number. So this is a n plus 1 to infinity. It's a union of all these things. And if certain point belongs to an infinitely many times, then of course it will belong to some of the aj greater than n. And therefore it belongs to this union. And it would belong to this union any n. The starting point any n doesn't matter, because no matter which n you choose, since it's infinite, so you can always belong to some aj that's greater than n. So any set here will belong to the bottom of the union. And also the any point that belongs to this union. This means that a infinitely often means that this for any n, for all n. Now I claim, so we just show that an infinitely often, then it belongs to the union for all n. And the opposite is also true. If it belongs to the union for all n, then it also means infinitely often. Because it's not infinitely often, then it will stop, the sample will stop belongs to certain n after n is too large. Right? And if you choose n too large, then the union after that will not contain that sample. But if you say this union for all n, then it means it has to be infinite. So this equivalent statement, these two are equivalent. That's what we have to observe. Okay, so this is equivalent. This is still not equivalent. Okay. And so instead of so let's consider this event. So let's just pick one n and then consider the probability of this one. So instead of that probability, let's consider complement of that one. The complement of the union is like Morgan's law. How does it change? Complement of the union, you can change the order of the complement in the union. Does it change? Does it change in this way? And you say that it's a union of the complement. By my weird information, I guess my answer is wrong. So you have to change this into the intersection. That's the De Morgan's law. So complement of the union is the intersection of the complement, and vice versa. If the complement of the intersection, then union of the complement. That's the De Morgan's law. And so let's evaluate the probability of this object. So we want to show that this probability of the union is 1, is going to 1. And therefore, if we show that probability of the complement,
voice is breaking.
I'm sorry?
I just hear the breaking voice, or rest of the people are also hearing?
Breaking noise?
Yeah.
Yeah, yeah, Prof, your voice is very low.
Yeah, and then
My
it,
voice is,
yeah, it's
Yeah, the audio is low as well for me.
let me, um, let me stop share. So my voice changed suddenly, or it has been like that all the time?
there's lots of like
It has been low.
and then
It
there's
has
a
been
lot of
low all the time.
yeah, all the time.
Oh, okay. Then voice only, voice is too low. I see. Let me stop the recording.